It is my very great pleasure to introduce our first speaker, Davud Rostam-Afschar. I hope I pronounced that correctly, from the University of Mannheim, and who's going to talk something I'm really interested in myself about earning while learning, so how to run batched bandit experiments. So David, I'm really looking forward to learning more about this. Thank you.
All right. So hello and welcome also from my side. I I'd like to share my screen now, and I hope you can see everything and hear me. Yeah, so it's really a great pleasure to be on this conference program. So thank you for having me, and I'm really excited to share some research on how to run batch bandit experiments and to do earning while learning with data. So we're gonna see in a second what batch bandit experiments are. And what I present is joint work with Jan Kemper, who is also in Mannheim, and we applied batch bandit experiments in a paper with Johannes Gaul, Florian Keusch, and Thomas Simons, who are all also at the University of Mannheim. So let's just jump into what batch bandit experiments are and why they're interesting. So probably really well known are the standard RCTs that are the gold standard of causal inference. And why? Because we can say something causally about some treatments. However, adaptive experiments allow earning while learning. And so because of this, there has been push to replace the non-adaptive randomized trials with bandits. And I'm from economics, but also in medicine, political science, survey methods research, education, psychology, and many other fields. These kind of adaptive experiments are now used more and more often. Also, practitioners use bandit algorithms, and the advantages are clear that you can optimize regret, so you can improve the outcomes of the participants, and also you can have a way to quickly find the best treatment arm in an experiment. And so how does this work? In contrast to standard randomized controlled trials, where the treatment assignment is fixed over time, these adaptive experiments use some algorithms to assign the treatment. And some popular algorithms are the epsilon first algorithm, the epsilon greedy algorithm, and the Thompson sampling, which we're gonna see a little bit more about in a second. So here is a set of papers from different fields that show you where, well, if you're interested in one of these fields, where you can find more research on these adaptive experiments, also including the paper Kasi and Zautman, which has been published in Econometrica, which I'm going to talk about a little bit later. The practitioners also write papers, so those guys are from Microsoft, Google, Facebook, Netflix, and so on. And so this is really an exciting field because also the practitioners are actually using those methods. And probably you have been part of a bandit experiment, perhaps without knowing. So to be on the same page, let's think about a little bit what bandit experiments are. So the term bandit comes from a slot machine in a casino, but here we can put ourselves in the shoes of a researcher, and the researcher has perhaps a drug for cancer patients, and the cancer patients consequentially and you don't know, perhaps as a researcher, which drug, if you have two drugs, A and B, which one of them works better to ensure survival of patients. So, so that's why you need to kind of learn which one works best by randomization. But if you randomize all the time for the complete experiment, lots of people, well, eventually will die, and that's causing a regret. So the questions that these adaptive experiments solve is, or the Bandit experiments actually also, which arm should you play in the next round when a new patient comes, and which arm performs better, arm A or arm B. And we're going to look at how this works more precisely using the algorithm by Thompson. So this is actually also fascinating because in the machine learning literature, the Thompson algorithm is a standard algorithm, but he invented that actually way before there was the widespread use of computers. So Thompson actually had exactly this problem in mind. How can I minimize the regret? And here is an example with 3 arms. So you see here 3 distributions, and on the horizontal lines you see the success rate of each of the arms. So from 0 to 100%. And then we have the second arm and the third arm. And on the vertical, you see the density. So it's a probability distribution. You can think of it in terms of Bayesian statistics as a prior distribution. And so in this example, the trials are a coin toss. So you have a binary variable, a 0-1 variable. Either the cancer patient survives or the cancer patient dies. So you want to reduce the regret from having people die. So the nice thing about the Thompson algorithm is that it not only has a model for the expected success rate. So you see here these vertical dashed bars, that's the success rate. And you see that the second arm actually has 90% success rate, so that's the best arm. So, but the algorithm doesn't know that. The researcher doesn't also know that ex ante, only ex post. So the idea is how to learn which one of the arms is the best one and avoid playing the wrong arms. Yeah. And so the Thompson sampling not only models the expected success rate, it also models the uncertainty about it. So if the distribution is more compressed, then you're more sure that this is going to be the right arm. So Thompson sampling works with 2 parameters only. So it's a really nice example to get into this literature. And the B here stands for the beta distribution. This is nice for Bayesian statistics because if you have a prior that is a beta distribution, also your posterior distribution will be better. So it's a conjugate prior. And the updating of your distribution works according to a simple rule. So if you take arm K and not another arm, then you update that arm that you took by the observed reward that you got. So if a patient survived, then your alpha K will be incremented by 1. And if your patient died, your reward is 0, and so beta is going to increase by 1. And you see here also that the total number of trials you play, that's the sum of alpha plus beta for each of the arms. That determines actually how precisely you measure the success rate. So here you see the mean, that's the share, the success rate, the share of successes, and that is determined by the sum and the alpha parameter, and the variance is decreasing, so it's more concentrated as you play more. So if you have more experience with one arm. So let's check out an example how this works. I know this has been recorded on YouTube, so I have prepared also already something on YouTube to illustrate this. And here, let's just start from the beginning. You see these 3 arms, and now they have different success probabilities. So the dashed ones are the true probabilities that the algorithm doesn't know. So this one is 35% for arm number one at the top. The second, the middle arm, has a success rate, a true one, that is 60%, and the third one has 40% success success rate that is then eventually to be found out. But the algorithm, Thompson sampling, has a better distribution that it is initialized at 1 and 1. So that's the two parameters, alpha k and beta k, and that's a flat prior. You see, the algorithm tells you, I don't know anything about what this success rate looks like. So it could be anything in between 0 and 100%. I don't know. Then once you play an arm, and here you randomly chose the middle arm, then you play once, and that was a success. So you got a survival. So your distribution changes. You update that. And then if you play that again, wow, another success. Great. So this is a really good arm. Now we got a fail. And so you see how the distribution adjusts to this. And so if you tried the middle arm a couple of times, then you might want to try also the top arm. And that was a fail for the top arm. So let's go back to the middle. That was a success. And then let's try the bottom arm and so on. And then with more experience, you learn about the success rate. And you see here how this success rate is going more towards the true success rate, actually, that is the dashed line. Yeah? So over time. And what is also illustrated here is that you see the middle arm is played much more often than the other arms, and that's because the algorithm wants to avoid playing the wrong arm. So if you let this run, you see it tries out a little bit, so it's learning by experience and updates that prior, and it plays many times the middle arm and not so much the other arms. And you can take those parameters to calculate the success rate. And here you see it comes pretty close to the true success rate. Yeah. So that's how Thompson sampling works. And we actually implemented that in Stata, which is a new comment that we introduce. And we are excited about trying that out. But there is more, actually, because, even though there is this push for adaptive experimentation, it comes with some problems. So, it was not available in Stata before, so that's why we implemented it. But also, it breaks the usual asymptotics, so you get wrong standard errors and wrong confidence intervals. Why is that? Because usually your treatment is going to be independent, but not so with the multi-arm bandits, because they actually, the treatment assignment depends on the history. So what the experience was determines how much of a share is going to be assigned to which of the treatment arms. And so there have been some statisticians who proposed a solution for this, which is called the batched OLS estimator. And we're going to take a look at how this works in a second. But first, we want to see what actually causes this problem. So here's a simple example for also, again, the Beta Bernoulli multi-armed bandit, so the two-arm bandit actually with Thompson sampling. And we run this for 10 batches, and each batch had 100 persons or observations. And so the problem is that if the two treatments, so think of two drugs, A and B, if they're performing almost equally well, so if the margin between them is close to 0, then you get what you see here on the left-hand side. Then you get not a normal distribution for the OLS estimator of the margin. So there is some probability mass missing here. On the other hand, the batch OLS estimator gets it right. So that's the solution to this problem. So to understand how this works, let's check out an example with a simple data structure. So here we have the number of observations and the selected arm in the beginning, we just uniformly assign the arms to each observation. And now the different thing to the standard multi-arm bandit is that we put the observations into batches. So here we have 4 observations in batch 0, and we don't observe the reward so far because we haven't run the experiment. And so this batch size actually makes this thing work, because then the asymptotics go over the batch size, which is independent, and the central limit theorem holds here. So that's the basic idea of the batched OLS estimator. And so once we run the experiment, we see, well, we got 1 survival and 3 death. So A could be the better drug, but let's run this further. So in the next batch number 1, we still have 50-50 assignment to each of the 2 treatments. Let's see what is the outcome here. We got survival for A and 1 for B. The rest are no survivals. So we have in total 2 times survival for A. So the algorithm could choose A as the potentially better drug, and assign more people to this treatment. And in fact, this was in this example a good choice, because 2 of those A observations, they actually have a survival. And then you can move on with this, and you get here a good success share. The true expected reward that the algorithm didn't know, but in the end wants to discover, is given here in the next column. And what you get with OLS is a approximation of this. So this estimates the expected rewards. So running the batchwise OLS gives you only for the first 4 observations an estimate, and then for the observations 5 to 8, another one, and so on. So you have batch-wise estimates. And here you see this is 0.5, because 1 who got the drug number A did not survive, and 1 did survive. And for B, it's 0 throughout. And here in batch number 2, you have 3 person getting drug A, and 2 of them survived. So you have 2/3 survival rate here. So with this, you can calculate some weights omega t, and these weights are essentially the number of observations assigned to each of the treatments. So here we have 2 people assigned to treatment A and 2 to B. So this is 2 times 2 is 4, divided by 2 plus 2, which is also 4. So square root of 1 is 1, so the weight here is going to be 1. It's more interesting here, because here we have an unequal assignment. So only 1 person got the B, so that's the one here, and 3 persons got the treatment A. So we have here 3/4 and the square root of it, and that's going to be the weight. So the weight then aggregates each of the estimates of the batched OLS. So all those margins are going to be aggregated using those weights. And here is the formula for the weight. So the NTK is the number of times that the comparison arm K was played in batch T, and NTB is the number of times that the baseline arm was played in the batch T. And the weight is calculated according to this formula. So Zhang and co-authors, they show that using this weighting results in a consistent and asymptotically normal estimator, which is what we want. Here is an example how to calculate the point estimate. So for OLS, it's pretty simple with a regression with a treatment indicator. And for batched OLS, this is just using also the weights, but you get here in this example the same results. From this, we can construct confidence intervals in a standard way. The only exception is that we have here this WT, and this WT is again composed of those weights. So we get then a correct coverage. So what we did is we programmed this for researchers to use, and that's a command that we called the bbbandits command. And it has three variables: the reward, the assigned arm, and the badge. And you can download this here on this website. You can get also some more information on this website about this command. And it actually comes in three subcommands. So one is to analyze the data, one is to simulate Monte Carlo simulations, and one is to interactively run those experiments because they are sequential. So let's check out an example. So this is taken from Kasi and Zautman, Econometrica 2021. And they look at 6 methods to enroll rice farmers via telephone. And they use something called the exploration sampling method for this NGO in India called Precision Agriculture for Development. And that NGO actually partners with the government to provide a phone-based, personalized agricultural extension service to farmers in, I think it was Delhi, if I remember correctly. And so the aim is to choose the best call method to enroll the rice farmers. And they had several treatments, so it's a multi-armed treatment. And those treatments are shown in this tree here below, but let's first check out what the outcome variable is, the reward. That's a binary variable for call completion. So it's 1 if the call recipient answered 5 questions asked during the call and 0 otherwise. And the treatments are you get an SMS alert 1 hour ahead of the call, and that's at 10 a.m. or at 6:30 p.m. Or you get an SMS alert 24 hours ahead, again at 10 a.m. or 6:30 p.m. or no SMS alert whatsoever, and just a call at 10 a.m. or 6:30 p.m. So the exploration sampling works similar to Thompson sampling, but it pushes a little bit away some weight to explore more than the Thompson sampling does. They got 10,000 valid phone numbers and used 16 batches. And each batch had a size of 600 telephone numbers, and the first one had 400. They run this in 2019, every other day, and it was completed the next day. So if you use the bbbandits command for this, you get this output in Stata. And here you see at the top the number of observations, that's the 10,000. And we have some calculations here. So yeah, please feel free to interrupt me if there are any questions. So here you see the actual mean reward. So that's the result they got. 1,804 calls were successful out of the 10,000, so 18%. And if they had new ex ante, which one was the best arm, they would get 19%. So it's a little improvement, but remember that if you have something, an experiment that goes about life and death for cancer patients, for example, then one more success can be really a lot. And if they would have played that in the fixed and balanced setting, they would only get 17%. Here you get the comparisons, the margins. So the mean reward is 16% for the baseline arm here. And the margins, you see that arm 1 was better than the arm 0 in OLS, and then batched OLS, so they differ slightly here. And here you get the confidence intervals as well, and the shares with which each arm is played. You can also visualize this in a coefficient plot using the bbbandits command, and it looks like this picture here. You can also see the sequential nature of this experiment by looking at the batch-wise shares of each of the treatments and the cumulative shares on the right-hand side. So this example shows some clear takeaways. So the best calling method is calling farmers at 10 a.m. after 1 hour ahead SMS message, and the worst one is calling them at 6:30 p.m. without a text message. And we saw the improvement already but it might seem small, but it's actually quite effective. It can save a lot of money to the program, or if you get some grants, you can save money for those who give you the grants. So we have expanded actually on this kind of experiment using the German business panel, which is run in Mannheim. And I'm also involved in this German business panel. And here our question was, how can we invite firm decision makers, because that's the target audience of this survey, to participate in the survey when we send them emails. So which is the best email message that we should send them so they participate? If you want to learn more about the German business panel, please check out Bischoff and co-authors, or Hack and the paper by Lukas Hack and myself about how this data look like, and you find them online. So here we have outcome variable that is also binary, and that's if someone clicked in the email on the link for taking the survey, then this is coded as a success, and otherwise it's a 0. So we took a look at different factors in the email, so components of the message that could enhance the starting rate, and those are personalization, so mentioning the firm name in the email, so inviting someone as a representative of a firm, or just using some generic salutation. Also using authority, so putting there some titles or not, the URL position at the top or the bottom of the email, emphasizing data protection or not, and also the message frame. That's something from Survey Research Methods. They say that you could plead for help to participate in the survey, or you could offer just to participate. So we wanted to find out which one works best. So we had 5 factors, and 2 to the power of 5 is 32 full factorial treatments, so 32 messages. And we wanted to see all of those, because we wanted to see also the interactions between the treatments. So we used 11,000 randomly selected contacts and assigned them to 15 batches from a list of 176,000 contacts. And we run this in 2022, and we used the burn-in phase. So the first 4 batches actually, and batches were weeks in our case, they were the standard randomized control trial with fixed arms. And then from batch 5, we used Thompson sampling. And here are the results. They just show you that you can run this also with many arms. And so if you're if you run a website, for example, and you have a spot to advertise, then you might have not only 32 arms, you might have millions of possible. Question is which one works best. So you can try this even with million arms. And here is a result showing the OLS and the batched OLS estimates and the confidence intervals. We also have here a clear winner. So one arm works really well. And here you see that after the first Thompson sampling batch, this has been assigned a larger share already. And then it also accumulated over time. So the clear takeaway is that we have a clear winner. Using personalization is good for inviting people to surveys. Using authority like titles also helps, at least in Germany. I would be curious how this works in other countries. And pleading for support is also really making the message a little bit urgent. That helps as well. So if you are interested in this, check out the paper. There are more results also on the interactions there. So what problem is actually solved with the batch bandit estimator is shown here. So here, what you see is the distribution, and we compare 2 arms. One has 50% chance and one 40%. And here, focus on the distribution. Now, as they become close, you see how this is not normally distributed. And that's exactly the problem of the OLS estimator. And if you watch the batched OLS estimator, you see that this is normally distributed throughout. So we also designed a subcommand of the bbbandits command to run own experiments, but in because of time reasons, I will just skip this and leave this to you to check this out. So here is an example how to run your own batched experiment. You can also use Excel for updating those rewards and then load them back into Stata. So that's really flexible, and you can update and run your batches. And we got some best practices then for analyzing this. With this, I want to conclude and wrap up. So researchers should report both the OLS and the batched OLS estimates and confidence intervals. The batched OLS inference actually is correct in the small margins case. So if the effects of the two drugs are really, really similar, which is actually often the case in medical applications. And OLS is more precise in larger samples. So you might want to check out both, and also the batch-wise OLS estimates. And with the batched OLS estimator, the asymptotics run over the batch size, so the number of observations in each batch and arm. And we recommend at least 50 to have asymptotics. You can also try 20, but to be on the safe side, at least use 50. So there's this crucial trade-off between exploration, so learning, and exploitation, the earning part. And from a statistical testing perspective, we want to have more observations per batch and arm. But from a regret optimization perspective, if we want to save cancer patients, we want to have as few observations and as few fails as possible. So we provide a tool for putting this into practice, and there has been and there is still an explosion of papers and applications in development economics, labor economics, biostats, health, accounting, finance, and other fields that use adaptive experiments. And but those experiments that are adaptive, they break the independence for the treatment assignment. So they break also by design inference. So the usual confidence intervals will not be valid. And researchers want the valid confidence intervals to make conclusions. So we offer the batch bandit command to get the correct inference and to analyze and visualize adaptively collected data. All right, so that's it from my side. So I hope you enjoyed this. Thank you for listening, and I'm curious if there are any questions. Thank you.
Thank you very much, David. That was a really interesting talk. You presented some complicated concepts very, very well. I have questions that I would like to ask you, but I think we're running a little bit slow on time, so perhaps myself, I'll send you an email and other people could contact you with their questions. But thank you very much for a very, very interesting presentation. I'll pass things on to you, Bosco.